Here is a concept map that I've crafted as a way to represent and summarize the key concepts and their relationships to one another from this week's chapter. This is my own representation and, as such, is not meant to suggest that it is the only way to do this concept map for this week's chapter. Although I've said this previously, do keep in mind that this concept map does adhere to some basic principles for concept mapping design. That is, key concepts are placed in circles, or what I might call nodes. Two nodes may be connected to one another via a line segment with a propositional phrase on that line segment to describe the nature of the relationship between the two nodes. Note that line segments have an arrow at one end to tell us how to read the relationship between the two concepts, i.e., from one node to another. As with most concept maps, we typically will find the main organizing node in the center or at the top of our map. Either way, it ought to be clear to others. So make it stand out in some way. Concept maps ought to be readable to others. That is to say, when reading a concept map, one ought to be able to read statements. When put together, a full reading of the map should tell us about the chapter, its key ideas, and how those ideas are related to one another. As you can see, this week's concept map is a bit more complex in comparison to the first one I showed previously. Don't let this throw you off. In fact, it will probably be the most complex one we see this term. This chapter, after all, is, perhaps, the most important one for the entire course. As many of you will be able to discern, I've once again used color to point out certain clusters in my concept map, but I've also used different shaped nodes. Some are oval, some have rounded corners, and some are squares. I've also used some shading for some different effects as well. For example, I have, generally speaking, placed important formulas into rectangular boxes and shaded them gray. The rectangular figures with rounded corners denote the big ideas from the chapter. I've used the ovals, shaded in different colors, to denote how different concepts are represented with special notation. The other nodes are, generally speaking, elaborations of the other nodes. I would encourage you to consider doing similar things when you do your future concept maps, if you have not already done so, just so long as you follow the basic principles of concept mapping. So let's begin. Roughly speaking, we can divide Chapter 2, Ways to Describe Data and Data Distributions, into two parts: measures of central tendency and measures of dispersion or variability. Let's start with measures of central tendency. So we'll be looking at the bottom half of our concept map. A measure of central tendency is, in a manner of speaking, the best way to describe your distribution. And in this case, we have three different ways in which we might describe a distribution. We can describe it through the average value. We can describe it as being the center value for the distribution, or the most typical value for the distribution. To calculate the average value, I suspect you might be familiar with this one. One would calculate the mean. And the mean has a formula. This is the first of many formulas that we'll discover throughout the course. And it's equal to the sum of all the values in the distribution divided by the number of values that are in the distribution. And as we can see, we would use different notation depending on whether or not the distribution is of a population or a sample. We would use the sum of all the distribution values divided by big N, which represents the number of values in the population, or we would use a small n in our notation if we're working with a sample. Let me say this one more time. We would use different notation depending upon whether or not we're calculating the mean for a population or the mean for a sample. And as we can see here, we would use the Greek letter mu if we're calculating the population mean, or we would use the notation x with a bar on the top of it to denote the sample mean. Last but not least, pertaining to the mean is going to be sensitive to extreme values. If you were to imagine a particular distribution and then were to add a very, very large number to that distribution, that very large number is going to affect the mean in some significant manner. In fact, it's probably going to make it larger. Another measure of central tendency is referred to as the median. And this value is going to be a number which strictly divides the distribution into two equal parts. Unlike the mean, we should take note that the median is not sensitive to extreme values. So if you have a distribution that has a particular mean, simply by adding one very large number onto your distribution is not going to affect the median tremendously so. To calculate the median for a distribution, we have to do a couple steps. The first step involves ordering all the data values from smallest to largest. After that, we need to find the middle value, and depending upon whether there are an even number of data values in your data distribution or an odd number of data values will affect how you determine the median for your distribution. If there are an even number of data values in your distribution, you'll find the two middle values in your distribution, once they've been ordered, of course, and then you'll take the average of those two middle values. If you happen to have an odd number of data values, it's just a matter of finding the middle number in that distribution. And that is your median. Moving right along, we have the third of our three measures of central tendency, and that is the mode. And the mode represents the most typical value in your distribution. In other words, it's going to be the number in your distribution that occurs the most. And we can look at different kinds of distributions, and in my concept map here I identify two particular distributions, one which is called unimodal and the other is called bimodal. And unimodal distributions are distributions where there is one mode in the distribution, that is one number that occurs the most. In bimodal distributions, these are distributions that have two values that occur the most in your distribution. So that's the bottom part of our concept map done. Let's turn our attention to the top half, which I've done mostly in green and refers to the concept of measures of dispersion or variability. Like the measures of central tendency, measures of dispersion or variability provide us with a number that describes other kinds of characteristics of our distribution. In fact, they tell us something about how spread out the values of the distribution are. And like the measures of central tendency, where there were three particular characteristics we could use to describe the central tendency of the distribution, we have, in our textbook anyway, three different characteristics that we can use to describe how spread out the values of a distribution are. And those ideas are variance, deviations from the mean, and range. The range is perhaps the easiest to calculate. It's calculated by taking the smallest value in our distribution and subtracting it from the largest value of the distribution. The thing is, a range really tells us nothing about how the particular values, all of the values in fact in the distribution, are spread out. It just says something about the smallest and the largest. We can also look at how all of the values in our distribution deviate from the mean. This, as it happens, is not particularly useful to us because in adding up all the deviations, we find that the value equals 0. Although this is not going to tell us how our distribution is spread out or varies, it will tell us if our mean has been calculated correctly. In our text, we're presented with three different ways to calculate deviations from the mean. We're presented with average deviation, average absolute deviation, and the standard deviation. We are going to focus on standard deviations for a number of different reasons. These reasons won't be discussed here, but suffice to say, mathematically speaking, it just makes more sense to work with the standard deviation. The last of our measures of dispersion or variability is referred to as variance, and there's a relationship between variance and standard deviation. In fact, if you know the standard deviation for a distribution, it's just a matter of squaring it to get the variance. And if you have the variance for the distribution, one simply takes the square root to get the standard deviation. One way of thinking of the variance is that it produces an average squared deviation. Just as we use special notation to calculate the mean, we have special notation for calculating standard deviations and variance. These are represented in the oval nodes that I have in my concept map. So starting with s squared for sample, this is how we would represent the variance for a sample. If you're dealing with a population, we would use Greek letters. In this case, it's sigma squared for the variance of a population. In dealing with the standard deviation, then, for a sample, we would use the letter S. And if we're dealing with a population, the standard deviation for a population is denoted by sigma. Note that when we calculate the variance, this will allow us to eliminate any positive and negative deviations. So if we were merely calculating deviations from the mean, which As you recall, when we add them all up equals 0, we'll eliminate some of those negative deviations, making them positive, and taken all together, it allows us to get a sense for how distributed the data distributions are. We have two more formulas to address within this chapter and concept map. We have a representation referred to as a conceptual formula for the variance. We also have another formula referred to as a computational formula to calculate the variance as well. Both formulas give us the same result, but one is a little bit easier than the other in terms of calculation. And not only should they give us the same results, they are referred to as being algebraically equivalent. Last but not least, at the top you'll see one remaining box that comes from the S for sample oval and the S squared for sample oval. And this is just a reminder that when calculating the variance and the standard deviation for a sample, we do have to modify our formula just a little bit. When calculating the standard deviation and variance for a population, we have to divide by big N, that is, the number of values in our population. When we're calculating the variance or the standard deviation for a sample, we need to divide by small n minus 1 instead. That is, n being the number of elements or data values in our sample distribution. And there you have it, our concept map for describing data and data distributions.